Hello friends, welcome back to yet another Facebook Live session brought to you by the JEE team here at BYJU'S. Well, today's is a mathematics session. It has been quite some time since we've had a math session, so we've got quite some catching up to do. We are still with 11th standard syllabus. We've seen a little bit of sets, relations and trigonometry in the previous math session, which was more than a month ago. So moving on, we are going to look at two very interesting chapters from algebra. So the first chapter of algebra, which incidentally doesn't appear in the NCERT textbook but is very important from our point of view, is quadratic equation, which is a chapter that is a part of a bigger chapter, which is theory of equations. So let me take you back to high school days when you were looking at algebra in a very different way, because algebra for you at that point was just solving systems of equations. It began with linear equation in one variable, moved on to system of equations and a little bit of inequalities, and then towards the fag end of your 10th standard, you had quadratic equations. You were introduced to this concept of quadratic equations and the method of solving a quadratic equation, either by factorizing or by using the quadratic formula minus b plus or minus the under root of the discriminant divided by 2a. So this concept is going to be built in quadratic equations and also extended to higher degree equations in theory of equations. So in quadratic equations, we are going to start by looking at what we saw in 10th standard, which is solving a quadratic equation either by using the factorizing thing when you can easily find the factors, or by looking at the quadratic formula wherein the discriminant becomes important. Then we extend that concept to identifying the nature of the roots. Based on how the discriminant behaves, we can say whether the roots are real and unique, distinct, or whether they are real and identical, or if there are no real roots. Furthermore, we look at relationship between these roots. What are the sum of these roots? What are the product of these roots? And do they have any correlation to the general form of a quadratic equation? Say you have ax square plus bx plus c is equal to 0, and if alpha and beta are the two roots of this quadratic equation, we focus on whether we can develop any sort of relation between the sum and the product. So you say alpha plus beta is equal to negative b over a, and alpha beta is c over a. So this is what happens in quadratic equation. These have some very interesting formulae, and some very interesting questions can be formed out of these. So they give you the sum of the roots, they give you the product of the roots, and then they ask you to find the roots based on the given quadratic equation. It's a very interesting set of questions which come into existence based on these relationships. This is extended in theory of equations to higher degree equations. If you have a cubic, what is the sum of its roots? What is the product of the roots, two taken at a time? What is the product of all the roots all taken at the same time? All these are very interesting relations which are extended from quadratic equations to theory of equations, and this becomes a very important part, not just in algebra but in almost every other sphere of mathematics, because algebra sort of is the binding element which holds a lot of branches of mathematics, be it calculus, be it geometry. Everywhere where there is an unknown to be found, you have to go back to the concepts of algebra. So that's why quadratic equation is quite an important chapter, and especially in your 11th and 12th standard days when you're preparing extensively for JEE, it's important that you get the basics of these algebra chapters right, not only because they fetch a lot of marks, but also because these chapters will have a lot of concepts that will be quite inbuilt into the problems that you will solve in chapters that you will be encountering in the future. So it's important that you understand the concepts of algebra and put them into great use by solving more and more problems and getting acquainted with all these concepts very well pretty early in the early stages of 11th standard. So let's get back to quadratic equations. So certain very simple problems which sometimes appear straight away in the main examination would be nature of the roots. I've already spoken about the nature of roots. So they might give you a quadratic equation and they say that the nature of the root is so and so, you have to find out the different coefficients such that the discriminant is either positive or 0 or negative based on whatever is the nature of the root. This is a standard kind of problem which might sometimes come in your main examination, or whose application might be there in the questions that have been posed in these examinations. So yet another very interesting concept which can be developed from what we've seen so far in quadratic equation is the graph of a quadratic equation. Now, why is the graph of a quadratic equation very interesting? Is because you will be studying about this particular curve in great detail in coordinate geometry. So the graph of a quadratic equation is nothing but a parabola. So when you have a quadratic equation of the form ax square plus bx plus c is equal to 0 with a positive or negative, the nature of this curve will change. So you have the upper parabola or the lower parabola based on how your a is. So ax square plus bx plus c is equal to 0 is not a parabola. Ax square plus bx plus c is a parabola. When you equate it to 0, you get the roots. That is the point where this parabola cuts the x-axis. Now, it's important to not just visualize these things, but get a very clear understanding of how these things behave. Because going forward, if you can kind of visualize this parabola and the nature of this parabola and whether it cuts the x-axis, touches the x-axis or lies above or below the x-axis, becomes very, very important in solving problems quickly. Sometimes you don't even have to lift your pen and write something on the paper, and you can straight away solve a problem if you just understand the nature of this particular graph. And this will and such questions will appear in chapters where, you know, which have applications of quadratic equations. And for example, if you're looking at chapters on inequalities, sometimes you will have to use the quadratic formula and the nature of its roots, and to visualize it using graph is very easy. So get a clear, sound understanding of how the graph of a quadratic equation looks and how this graph will behave depending on the different nature of the discriminant. It's a very interesting concept, and questions do come from this in the main and the advanced examination pretty often. And as I've already told you, these find application in other chapters which you will be encountering in the coming days. So we've spoken about the quadratic formula, the discriminant, the nature of the solution, nature of the roots, and also the graph of the quadratic equation. Now, when we speak about the advanced examination, questions that come from quadratic equations will not be very straightforward questions where they give you a quadratic equation, ask you to find the roots, or based on the nature of the root, ask you to find a few coefficients. No. Questions tend to be a little tricky, and they tend to they will tend to test your knowledge of other concepts as well. Now, one very famous question which came a few years ago in one of the advanced examination was a question on quadratics that involved the modulus function. It was something like the modulus of x the whole square plus 5 modulus x plus 6 is equal to 0. How many roots does this particular equation have? Now, such questions require a lot of analysis. Now, there are multiple ways to approach this particular question, and inevitably, if you know the concepts well, you can reach the solution very easily. So mod x square plus 5 mod x plus 6 is equal to 0. If you blindly do this particular question, if you, let's say, consider mod x as some other variable t and say t square plus 5t plus 6 is equal to 0, and try to solve this particular question, you'll get t plus 3, t plus 2 is equal to 0, t is equal to negative 3, t is equal to negative t would be equal to negative 3 and t would be equal to negative 2. So you might say that, okay, mod x is negative 3, mod x is negative 2. And you might say, okay, now if mod x is negative 3, mod x is negative 2, there are 4 answers possible because mod would mean a plus or minus. But that's where analysis comes into picture, because mod of x cannot be ever negative. So if mod x is negative, that means it doesn't have any solution. So this is the procedural way of getting to the solution. But there are shortcuts which can be done in much easier ways if you actually know graph of quadratic equation. Now, mod x square plus 5 mod x plus 6. Now, mod x square is a positive term, 5 mod x is a positive term, 6 is a positive term. All of them put together is positive. So a positive can never be equal to 0. This means that this would have a graph which lies above the x-axis completely. It never touches the x-axis, which means that even without lifting your pen, you can say that mod x square plus 5 mod x plus 6 is equal to 0 has no solution at all. So these are certain interesting ways of solving problems that you must develop, and they will come only when you have a very sound understanding of the concepts. If you understand what quadratics stand for, how the graph of an equation will look like, what the modulus function stands for, what equal to 0 means, if you understand all these things, that is when you will be able to solve quadratic equation problems very fast in examination hall without actually resorting to the methodology of solving this particular problem. So the modulus function and the greatest integer function, these are two functions which normally find application across every domain of mathematics in 11th and 12th standard. So in quadratic equations, there are problems which come with a modulus function involved in it or with a greatest integer function. So for example, there was this problem which appeared a few years ago, which was like, let's say a -3 times x minus the greatest integer of x plus 2 times x minus the greatest integer of x the whole square plus some constant equal to 0. You have to solve this quadratic equation and find the value of x. So it is a little difficult to solve this particular problem, because how do you solve for x minus the greatest integer of x? So then what you do is you always go for a replacement. You substitute x minus modulus of x to be some value and then solve the quadratic in terms of that other variable, which is, let's say, a t or a u or whatever you want to call it. And then you get a solution for that particular variable. Like just in the previous case, we got, when it was mod x the whole square plus 5 mod x plus 6 is equal to 0, we got the value of t, which was a replaced variable for mod x, to be -3, -2. And then we thought, okay, this doesn't make sense. That's where the analysis comes into picture. Similarly, when you substitute x minus mod x to be equal to some other variable, let's say p, q, r, t, whatever you want to call it, you get a solution. When you get a solution for this particular t, that is where your analysis sets in. Now, what is x minus the greatest integer of x? X minus greatest integer of x can only lie between 0 and 1, because the greatest integer of an integer is that integer itself. So x minus greatest integer of x, if x is an integer, is 0. X minus greatest integer of x, if x is not an integer, can at max be 0.99999 bar, but never be equal to 1. So there is a range between which this particular value lies. So when you get the answer for t, which was your replaced variable, or p, q, r, s, whatever you've called, you have to go into this analysis phase. So that is very important in solving advanced questions from quadratic equations, because as such, quadratic equations is a very simple, straightforward concept. So the examiners are going to set papers wherein there is analysis involved. You get a solution, you solve a simple quadratic equation, arrive at a solution, and then you analyze this particular solution. That analysis plays a vital role in getting the answer correct or wrong. So this analysis is where all your understanding of the concept comes into picture. Yet another different type of problem in quadratic equation, wherein you will not have to replace or substitute a variable and solve, but still analysis is important, is when you have under roots appearing. So if you have under root of something plus 5 is equal to some other term, the way to solve this problem is to take the constant terms or the terms without the root to one side and separate the roots on one other side, and then you square both sides, and then you get a beautiful equation. You solve the equation, you arrive at the solution, and you say that this is the solution to the problem. No. What has actually happened is when you square an expression, you're actually changing the domain of the expression. Because let's say you had under root of 1 minus x square. Now, what is the domain of under root of 1 minus x square? You cannot put any value of x such that 1 minus x square will become negative, because we still don't know what is the negative root of anything. So 1 minus x square has a domain which will lie between -1 and +1, because if you put anything more than +1, 1 minus x square is going to be a negative number, or if you put anything less than -1, 1 minus x square is going to be again a negative number, and this negative square root of something, we still don't know what it is. So what you did when you squared is you converted the equation from the square root of 1 minus x square to just 1 minus x square. Now when you solve this particular equation, you might get a solution x is equal to 5, which is okay for 1 minus x square, because if x is equal to 5, 1 minus x square equal to negative 24 still makes sense. But the square root of negative 24 does not make sense. So if you get a solution x is equal to 5, you have to put it back in the original question that was given to you and then see, oh, does the solution make sense or not? If the solution does not make sense, then the actual answer to the question is it does not have a solution. So these are tricky things in quadratic equations which people almost always tend to go wrong in. And while question paper setters will set the options in such a way that one of your wrong answers will be an option, and you will end up ticking that option and then go wrong. So it is not only a waste of time, you wasted useful 2 minutes on solving that problem, you have ticked the wrong answer and you've lost marks. So this is sort of disastrous because you've spent time, you've got the answer almost correct, but you've marked the wrong answer and ended up losing marks instead of gaining marks. So always make sure that you do a little bit of analysis in questions which come from quadratic equations. If a question is very simple, straightforward, and absolutely easy to do, you must always have this second thought that, am I missing something? Hey, this is the IIT JEE advanced examination. The question cannot be this simple. There is some twist that I am missing, and that twist or the trick that was said by the question paper setter will come into your notice only and only if you analyze the answer that you've got. So it's very important that in quadratic equations, you always analyze the answer that you've got. You go back and check your answer and see if the answer makes sense. Sometimes without any mistake in the procedure, you will reach rubbish answers because the answer will be something that will not satisfy the given question. So this is very important in quadratic equations. So I've been talking about negative root of a root of a negative number. So I just now said that we still don't know what the root of a negative number is, but that is where complex numbers come into picture, which is a direct consequence of quadratic equations. So far we looked at nature of roots. We said the nature of roots can be real, they can be distinct, they can be similar, and then we said they might not have real roots. So if they don't have real roots, it just means that my discriminant is negative and I have to take the square root of a negative number, and I don't know what the square root of a negative number is till I have encountered this chapter on complex numbers. Suddenly in complex numbers, they're going to define the root of -1 as iota or I, and then the whole new world of complex numbers become open to you. So complex numbers is yet another very beautiful, interesting, important chapter in algebra, which will expand your dimension in mathematics, and it will take you into a whole new world of complex numbers. It will take you out of real numbers into a different world. Now, complex numbers is something that you've encountered for the first time in your 11th standard. So it starts right from the basics. You look at what is a complex number. The complex number has a real part, has an imaginary part. So you are going to play with the real part, you're going to play with the imaginary part, and then you're always going to consider them separately. Never mix the real and the imaginary part. And then you look at new terms. You look at what is the modulus of a complex number. You look at what is the argument of a complex number. You look at what is the conjugate of a complex number. You look at all these beautiful things. Now in physics, even in 11th standard, you've been introduced to the concept of vectors. Look at complex number just like you look at vectors. You have two components for a 2D vector. You have the I component and the j component, and you never ever mix them. If you have 5i plus 6j and you have 7i plus 11j, if you're being asked to add these two vectors, you add the i's separately because they are the vector components in the x direction, and then you add the j's separately because they are the components in the y direction. So you add the x's, you add the y's, and then you get your resultant vector. Similarly, you add the real parts, which is going to be your real axis, and then you have the imaginary axis. So you add all the real parts together, you add all the complex parts together, and you get the resultant complex number in addition. So you always consider the real and the imaginary part separately when you have to do a few operations on complex numbers. Modulus of a complex number is nothing but the distance of a given complex number on the Argand plane from the origin. It is nothing else. but the magnitude of a vector if you're going to consider a complex number as a vector. So Argand plane, Argand diagrams, yet another important concept. So it's a very fancy name given to an xy plane where the y is the imaginary axis and the x is the real axis. So all these are new concepts that you've seen, you've understood, and you start playing with these things. Number of questions come from complex number in your advanced and your main examinations. They're very simple, straightforward problems. Most of the time they expect you to have a fine understanding, sound grip on these concepts, and because these concepts are introduced in 11th standard, it is very easy to get this hold on this concept, because of course you've not seen anything before and you don't have to go back and look at your 10th standard textbook or before to remember things. Everything is here in your 11th and 12th standard curriculum. You just open it, it starts right from the beginning, and you go gradually increasing your difficulty level, understanding more complex concept in complex numbers, and then you build your whole arsenal to fight any question that comes from complex numbers. So these are some very simple concepts: the real imaginary part, what is a conjugate of a complex number, or what is the argument, the modulus, and all these things. The Argand plane, rotating a complex number in the Argand plane, what happens when you rotate a complex number by 90 degree, by 180 degree, or by some any angle that has been specified in the question paper. All these things are different sort of things that you experiment with in complex number. But then when it comes to your IIT JEE advanced examination, these concepts are not enough. You have to move one step further from this and look at complex number in a holistic point of view. I've already told you that complex numbers are very simple, similar to vectors. Just like you can draw a vector. So two vectors would describe a line segment, so which has a starting and an ending point, and both these points are represented using position vectors of their end points. Similarly, on the Argand plane, you can represent straight lines and their end points will be represented by two different complex numbers. So you will have to write the equation of this straight line in complex number form. So we will extend complex numbers to geometry. We will look at straight lines in the Argand plane. We look at circles in an Argand plane. What is the equation of a circle in an Argand plane? What is the equation of a straight line in an Argand plane? All these things. But all these are concepts which are a little advanced. So if you've learned 11th standard complex numbers, you are not in a position yet to look at straight lines in an Argand plane or circles in an Argand plane, because before doing that you will have to actually go to coordinate geometry and look at circles in the xy plane. You will have to look at straight lines in the xy plane, understand the equations of these from a coordinate geometry point of view, and then come back to complex numbers and look at straight lines and circles on the Argand plane. And all these are very interesting concepts. It's just direct extension of what you've learned in coordinate geometry onto the Argand plane and in the complex number domain. So it's a very interesting concept, but these concepts do fetch a lot of questions in your advanced examination. Year after year, I've seen questions which are geometry plus complex numbers. These very interesting questions, but it's just important that you go through coordinate geometry very well and then understand complex numbers and then merge these two branches into a beautiful combination which fetches you marks in your examination. Moving back to complex numbers devoid of geometry, there are a few more concepts in complex numbers which are quite important. And the basis to all these important concepts is something called as the Mobius Theorem. So now if you have a complex number and you have to raise the complex number to a power, a very interesting theorem comes into picture, which is the Mobius Theorem. But before going into Mobius Theorem, we'll have to look at representing complex numbers in forms other than what we know. We know 5 plus I times 7 or 7i is a complex number. But this is the rectangular form of a complex number which can be easily represented on your Argand plane. There are different forms. Now, a very common form which is a replacement for the rectangular form is the polar form, wherein you represent a complex number in terms of its magnitude and its argument. So you represent a complex number saying this is at this distance from the origin, which is the magnitude, and it forms this angle with your positive x-axis. So that is nothing but the argument. So the modulus and the argument r and theta are used to represent your complex number in the form r times cos theta plus I times sin theta. And this is nothing but your complex number in the polar form. And this complex number in the polar form comes handy when you're supposed to take the power of a complex number. If you're supposed to take 5 plus 7i the whole square, it's very simple. You can say I will use the formula x plus y the whole square. But what if you are supposed to take 5 plus 7i whole to the power 104? I don't know what is x plus y to the power 104, but using the Mobius theorem, if you write 5 plus 7i in the polar form, which is r times cos theta plus I sin theta, and raise the whole thing to the power 104, very easily you can say that this is r to the power 104 cos of 104 theta plus I sin 104 theta. That's it. So de Mobius theorem is a very, very useful theorem when you're supposed to take the powers of a complex number. These are also very important, very interesting when you're supposed to take the root of a complex number. The Mobius theorem will say that one of the roots of the complex number is going to be r to the power 1 by n cos of theta by n plus I sin theta by n. This is going to be one of the roots of the complex number, and using this we will look at a very beautiful concept, which is the nth root of unity. And the nth root of unity, specifically the cube root of unity, will appear across different subjects in mathematics, different chapters of mathematics. You go to determinants, you go everywhere, you look at this cube root of unity, which is normally represented using omega. So that's a very, very important concept again, the cube root of unity. The properties of these cube roots of unity are also pretty important, and they will also find a lot of application in your examination, not just in this chapter on complex numbers, but also in different other chapters on probably matrices and determinants, sometimes in calculus as well. So it's very important that you understand how do we compute the cube root of unity in the complex number domain, and also draw these on the Argand plane and beautifully visualize how these things appear in the Argand plane. So very interesting concept, quadratic equations and complex numbers. Definitely not as complex as the name suggests, very simple concepts, requires you to solve a lot of problems and get a sound understanding of the nuances of this particular subject. As much nitty-gritty as you understand, the better. You understand more and more minute details, it will always pay off, because a small thing might be something which is going to be the difference between you scoring 4 marks in a question or getting a -1 mark. So it's very, very important that you understand these concepts in great detail and enjoy the beauty of quadratic equations and complex numbers. It's a Friday evening. I know all of you must be tired after a hectic week in school, and I'm not going to keep this session any longer. But yeah, before I sign off, let me take a few questions in case my viewers have a few questions for me. So let me see if my viewers have questions. Okay, here I have a few questions coming in. Equation of a line in a complex plane. Could you explain it briefly, asks Abhay Singh. Well, Abhay, this is not a session where I can actually go on and explain concepts for you. In case you want to understand these concepts better, the best way to do it is on our app. So in this particular description on the video, you can look up and you'll find the link to download BYJU'S the learning app in case you've not done it, and you can subscribe to our material and you can go and look at the chapter on complex numbers. Very beautifully explained how to get the equation of a straight line in the complex plane and play with it and solve problems. So there are a number of materials available out there where you can go and look at complex numbers and all the different concepts which are there in complex numbers. But if you feel that video learning is the best way to understand concepts, and if you feel that video learning will help you grasp these concepts and help you understand them better, then always subscribe to BYJU'S the learning app. And in the app, we've given you immense amount of material, so you have a lot of practice problems. You have the best teachers teaching you these things online, and then you can anyway write back to us and we'll give you detailed solutions. So Abhay, I'm sorry I'll not be able to explain in detail because there's a big time constraint. I have to stop in another 2 minutes. So you can definitely download our app and look at the content that is given in our app. The next question which is there is, how important is the cube root of unity? Well, as I was speaking during the session, I've told you that cube root of unity is a very important concept. How do you get the cube root of unity? You write 1 in terms of cos plus sine theta, I sine theta, and then take 1/3 and raise it to the power 1 by 3, use the de Mobius theorem and solve this particular thing to get the solution. How is it done? Again, you can refer to the BYJU'S app where we've solved the cube root of unity in a great detail, and you can find the solution to this. But how important is it? How important is the cube root of unity, and how important are the properties of the cube root of unity is a very important thing, because in different chapters, let's say chapters such as matrices and determinants, you will have questions which will involve the cube root of unity. You will get a determinant which is in terms of all the cube roots of unity. So in order to solve this determinant, you'll have to use the properties of the cube root of unity. Sometimes you will have questions in calculus where you will have to integrate some expression which has cube root of unity in it. So in order to integrate this expression easily, you'll have to use all the properties of cube root of unity. So understanding how cube root of unity behaves is very important. And it's not rocket science. There aren't too many things that are there here. The properties of cube root of unity are very simple. 1 plus omega square is equal to 0. And the cube root of any cube root of unity, be it 1 omega or omega square raised to the power 3, is equal to 1. All these are the simple properties that you have in the cube root of unity and nothing else. And using these properties, you can solve any problem which comes from cube root of unity. Cube root of unity is an important concept. How does it come into existence? Why are these properties there? What is the relevance of these properties? These are things that you have to explore in the chapter on complex number. And of course, their applications will be found across different domains of mathematics. And yes, cube root of unity is indeed a very important concept. I'll take one last question, and with that I'll be closing the session because it's already half an hour. My throat's almost dry. It's a Friday evening. So this last question is on quadratic equations, and the question that has been opposed by Dhruvil is that how important is the nature of roots? So the nature of roots, I have told you, is quite an important concept in quadratic equation, not just from a quadratic equation point of view, but also in complex numbers. Sometimes a question which will appear like a quadratic equation question might actually be a complex number question because the nature of its root is complex. So if you have a good understanding of the nature of the root, the first thing that you would do as soon as you look at a quadratic equation is identify the nature of its roots. Does it have a discriminant which is greater than 0? In case the discriminant is greater than 0, then the roots are distinct and you have two real roots. If the discriminant is equal to 0, then you have identical roots, but they still are real. Now if the discriminant is negative, that means you have to solve this problem from a complex number point of view. So you see the connection between quadratic equations and complex numbers. That is precisely the reason why these two chapters are being discussed on the same day, because these chapters are quite closely related. Also, nature of roots are important when you're looking at the graphical representation of a quadratic expression. So if your discriminant is negative, this means that the graph of the quadratic expression, which is a parabola, will never touch the x-axis because you don't have any real roots, which means in the real world that parabola is never cutting the x-axis. So nature of roots, very, very important for multiple reasons. One, it will help you analyze the problem better and make you understand whether this problem has to be solved from a quadratic equation point of view or a complex number point of view. And two, when you're looking at graphical representation or vice versa, you have a graphical representation of a quadratic expression and you have to determine the nature of its roots, you can look at the graph and say, okay, it cuts the graph at 2 points, two real roots, discriminant greater than 0. It touches the x-axis at 1 point. Oh, it has only one. In fact, it has identical roots and the discriminant is equal to 0. Doesn't touch the x-axis at any point. The nature of the roots is complex. So it's very important to have a beautiful understanding of all these different concepts that we look at quadratic equations and complex numbers, and then you will enjoy the beauty of algebra and be able to apply all these concepts across different domains of mathematics. I hope you will put in a lot of efforts, look at BYJU'S app for quadratic equations and complex numbers, and have a great time preparing for these two beautiful, very basic algebra chapters and enjoy mathematics. I'll see you soon with another session on different topics of mathematics from JEE examination point of view. Till then, have a great time, prepare well, enjoy your weekend, and I'll see you soon. Bye-bye.